So, we are discussing about multi-electron atom. So, atomic structure we have seen that whether in that atom whether one electron or more electron, but its structure is same for all atoms. So, that means this atom is having a nucleus and in that nucleus proton and electron neutrons are there and electrons are revolving in different orbit. Orbit is circular and elliptical, it is mixed, and the orbit or orbitals of atom where electron can revolve, electron can stay. So, that are specified by quantum number. So, n equal to n is principal quantum number, n equal to 1 is basically k shell, n equal to. So, for k shell another quantum number this L. So, it for n equal to 1 it can take value 0 to 1. So, n equal to 1, so L equal to 0, L can take value 0 to n minus 1. Okay. So, this under k shell, so this L equal to 0 is S subshell or S orbitals. Okay. So, then another two quantum number, this space quantization, due to space quantization magnetic quantum number ml, it can take minus L to plus L or plus L to minus L. So, this for L equal to 0 ml will be 0. Okay. And then spin quantum number, for that this S equal to spin of the electron. So, S one has to write for, if it is for one electron, so it will be half, but 2 electrons, 3 electrons, 4 electrons. So, what will be the S? Similarly, for L also, that I will already I have discussed. So, another quantum number ms. So, let us not write here. So, this ms equal to for single electron, it is plus minus half. Okay. So, these 4 quantum number is used to label the energy levels, as well as one can say to designate, to define the state of the electron. Okay. So, what I want to tell that we have now, it is known this for n equal to this k shell, n equal to 2, this is L shell, this for n equal to 2, this for n equal to 1, this is L equal to 0. So, under L cell, so there are subshell S and P. Okay. So, this L equal to 0 and L equal to 1. Okay. Then M shell, SPD. So, corresponding L equal to 1, L equal to 0, L equal to 1, L equal to 2. Okay. Similarly, n shell, okay. So, for its S, P, D, F, S, P, D, F, okay. So, this for this L equal to 0, L equal to 1, L equal to 2, L equal to 3, right. So, now for a particular NL value, so here, so each cell it contains how many electrons? It contains how many electrons? 2n square electrons. It is basically 2n square electron. So, it is equal to for each n, so it should be equal to 2 into for each subshell 12 plus 1, for each subshell 12 plus 1, and then 2 is coming from this MS. For particular L value, it can take 2 value of MS. So, this 2 is coming from here. So, for say M shell, n equal to 3. So, 3 means 18 electron. Now, it has basically one has to sum over L. So, L equal to 0, L equal to 1, L equal to 2. So, for L equal to 0, so it will be 2 electron 2, and then L equal to 1 6, 2 6 8, and L equal to 2 is 10. So, 8 plus 10 is 18. So, this n equal to 3 is 18. So, one has to sum up for each orbitals. So, that means this K shell, it can take 2n square, basically is it can take 2 electron, this can take 8 electron, okay, 2 plus 6 8 electron, this can take 18 electron. Similarly, one can 18, and this L3 means 6 7 14 and 18 32 electron, okay. So, this is the atomic structure. It has cells, subcells, and electrons can put in the structure. So, for one electron that I have discussed, that n equal to, so it can be n equal to 2 3 4 and L equal to 0 1 2 3, okay. So, it can go anywhere. Now, two questions. Now, question is what will be the minimum energy of the electron or of the atom. So, that is called ground state. Ground state of atom, and another is called excited state. Okay. Excited state. So, ground state and excited state means electron can be at any orbitals, okay. So, it will have definite state, but whether that state is ground state or excited state. So, rule is that, or energy expression tells that smallest n and smallest L, okay. So, that will be the quantum number for lowest energy, and if you go higher n and higher L, or for a particular n, lowest L will have the minimum energy and highest L will be the higher energy. So, L is increasing, energy is increasing. Okay. So, similarly for n also. So, that way one can find out, tell which one is ground state. Similarly, now here one restriction we are putting that in one cell how many electrons can stay. So, that already we have mentioned here, and that is based on Pauli exclusion principle. Pauli exclusion principle is that each electron will have the distinct this number NL, ML, MS, and it will not be same for 2 electrons, okay, based on that. So, this distribution of electrons in atom has come, okay. And energy wise, that expression energy En, I have En equal to minus mu z square e to the power 4 by 2 n square h cross square, okay. Enl equal to En 1 plus z square alpha square by n square, this n by L plus half minus 3 by 2, 3 by 4. Okay. So, this is the energy, and this from here you can tell the energy of different orbitals. So, this what I want to emphasize here. So, this we have found for single electron system. Now, if multi-electrons, if more than one electrons if you put, so atomic structure, overall structure is same, only its energy of different orbitals will be different. For one electron, whatever, for second electron, if we put second electron, so its energy will change, but the structure of the atoms remains same, means it has orbitals. Only the energy separation between the levels or penetration of energy levels or sequence of the energy levels for one electron system and for 2 electron, 3 electron system. So, that sequence may be affected in some extent, but it is not abrupt, it follows some rule, and there are reasons why there will be penetration of energy levels or deviation of the normal rules of energy levels following this one. So, this because of some other reasons. Okay. So, here we have not, whatever here I have mentioned, we have not considered any interaction. We have not considered any interaction like LS coupling. We have not considered. We have not considered, yes, mainly LS coupling, that is the origin is magnetic interaction, that is not considered here. When we will consider that one, so then J will come. Okay. So, so this will be the one reason for the deviation of this regularity of energy level following this energy formula. And in case of multi-electron, so what about the consideration for this derivation. So, we have to consider something more, because here only one electron. So, interaction between electron and the nucleus, Coulomb interaction, Coulomb force act on that. Now, if you put second electron, then electron some interaction will be there, repulsive force. So, that one has to consider, okay, for multi. So, starting from the single electron system, we can go for multi-electron. So, we have to correct this formula, okay, following some additional effect. So, immediate effect is one electron is there. So, there is no electron interaction. So, if I put another electron, okay, so there will be electron repulsive, that is Coulomb force also, it is a repulsive force. So, that one has to consider. So, that is considered is some Hartree Hartree-Fock method or Hartree method, HARTRRE Hartree method. So, in that method for multi-electron system, he considered the spherical distribution of the charge. So, he considered the average. So, for single electron, just direct Coulomb interaction, electron and nucleus. Okay. Now, if put second electron, so instead of this, so we will have two Coulomb interaction, electron nucleus and electron. So, Hartree, he considered this overall this potential, okay, spherical potential, considering this nucleus and the surrounding electrons, okay, keeping one electron. So, what will be the effect of other electrons? So, nucleus have that Coulomb interaction, that is there. Apart from that, if more than one electrons, so due to other electron, what will be the effect on this electron? So, that was considered as a spherical, that is average spherical potential was considered. Okay. So, that effect will be introduced here. Okay. So, because of this kind of additional interaction, so what I told that that arrangement of the energy levels following this energy expression. So, in some cases it will deviate. Okay. So, that one has to consider for multi-electron system. So, I have atomic structure, I have many cells, subcells. Now, if I put one electron, that is fine. So, this hydrogen atom, one electron. So, one electron. So, I have basically, so let me first see how many orbitals we have. Okay. So, for n equal to 1, I have 1s orbitals, n equal to 2, so I have 2s, then 2p, then n equal to 3, so I have 3s, 3p, 3d, n equal to 4, I have orbital 4s, 4p, 4d. Okay. Then n equal to 5, I have orbitals 5s, 5p, 5d, 5f. So, I think 4s, 4p, 4d, 4f also is there, 4f. Similarly, 6x, 6p, 6d, 6f, okay, 7s, 7p, 7d, 7f, etc. Okay. So, if we are not going f, g, h, I, we are not going because we do not need that many cells, subcells or orbitals to put electrons in case of whatever available known atoms are there. So, these are the available orbitals. So, I can put electron at any places. Okay. If I want to put one electron and at ground state minimum energy, so I have to put here one electron. Okay. One electron I have to put here. So, if I take second electron in case of helium, so for minimum energy for ground state, so I can put one mode here. Okay. So, basically 2 electron I can put. Now, third electron I cannot put here as for Pauli exclusion principle, this maximum 2 electron I can put. So, I have to go for next one. So, that will be the ground state for lithium. So, this is 2. So, this for lithium 1 is 2, 2 is 1. So, for beryllium 4 electrons. So, I can put here 2. Okay. So, this way then beryllium, then boron 1 more electron here, then carbon. So, I can put 2 electron, then 3, 4, 5. So, up to 6 electron I can put here. Okay. So, that is the electronic configuration of neon 10 electron, neon 10 electron, 2 to 4 and 6 10 for neon 10 electron. Okay. So, this way we can put electron one after another, and for ground state. So, I have to find out the minimum energy level from I have to fill the energy level of minimum energy. Okay. So, this way one can fulfill. Okay. So, now here rules are there to get the minimum energy. As I told, this sequence of the energy level is slightly different for multi-electron system. So, if I scale, so it is so this for 1 is, if this is the basically if I think I should draw here, if it is, say it is 1s. Okay. So, I should write 1s here. So, 1s, and 1s have again it has 2 level for ms plus half and ms minus half. Okay. And then for second energy level is 2s. So, I can put 2s again it has 2 level. Okay. Plus half minus half. Then I will have energy level 2p again 2p have 3, 2p will have actually 2p, now 2p have 3 ml. So, I will get basically, let me short it. So, 1, 2, 3, okay. This ml plus 1, 0, minus 1. So, this for ml depending on ml, and this basically for ms. Okay. And now for ml here again each one will be splitted into 2, okay, based on ms. So, it has 1, 2, 3, 4, 5, 6, it can take 6, this can take 2, this can take 2 maximum electron. So, this is 2p, and then I will come to 3s. I will come to 3s, 2p, then 3s, okay. Then I will go to 3s, 3s. So, 3s have basically 2, and then I will come to 3p, I will come to 3p, 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 and then I will come to 3d. Okay. So, this way I can arrange the energy level. Now, here next I will 3d, now 4s. So, now this 4s, where this 4s will be? So, next, so 4s is supposed to be here, n is higher, but it is not the case. 4s is really, it is below the 3d, so it is the 4d. So, I should use this one. You see, this will be the 4s. So, this 4s, the energy of this 4s, that is lower than the 3d level. Now, it is deviating, right, from normal sequence as per this energy expression. So, this, because in multi-electron system, because as I told, this some other interaction will be present, because of that this deviation. So, what will be the sequence of the energy levels? So, that's one can follow this building up principle, building up principle, building up principle. So, it is called also Aufbau principle, Aufbau principle. So, Aufbau principle, also it is called Aufbau principle. So, it is telling, if you just follow this arrow, okay. So, if you, so these are the sequence for the lower energy level to higher energy level. So, 1s, then 2s, then 2p, then 3s, then 3p, then 4s, okay, and then 3d, after that then 3d, after that 4p, after that 4p, okay. So, that way one can go ahead. So, so this the one can follow this building principle, Aufbau principle. So, following this one can put the electrons for ground state, one can put the electrons for ground state. So, so now either this energy level, following the energy level, one can put multi-electrons in an atom, okay. And now it is easy if I just follow this building principle, Aufbau principle. So, this principle based on some experimental results, but it comes from the theory, as I told, that one has to consider other effect rather than whatever for single electron system, whatever we have considered. If we consider other effect, so then this type of irregularity in energy levels comes, means one can explain the irregularity of this energy level arrangement. So, if so, so now if I know this sequence, so for any number of electron, one can find out the configuration. So, for hydrogen 1 electron, so its arrangement is like this. Okay. Helium 2 electron, C1 H2. For lithium 3 electron, so it is 1 H2 2 S1. For beryllium 4 electron. Okay. So 1 H2 2 S2. Okay. So similarly, if you go for neon, it's 10 electron. So one can 1 S2 2 S2 2 P6. Okay. Then if you consider say sodium 11, so 1 S2 2 S2 2 P6 3 S1. Then if you go for vanadium it is 23. Okay. Now it will come 1 S2 2 S2 2 P6 2 P6. So it is neon configuration, and then this 10 electron, then I have to come 2 P6 then 3 S2 then I will come 3 P6 18 3 P6, then 4 S2 So then it is, I think, 10 20, and then 3D, then it will come 3D. Okay. 1 S2 2 S2 2 P6 3 S2 3 P6 3D10 instead of 3D. So it's 4 S2, and then rest of this it's 3D. Okay. So 3D 3. Now for chromium, next one, chromium 24. Apart from this up to this. Okay. Now 4S, its configuration is 4S1 and 3D5. Instead of 4S2 3D4, we write 4S1 3D5. So here is for when the subshell is or orbitals, it's when it is half filled or full filled. Okay. So it is telling there is a reason, as I will tell you the reason. So here what we consider this, for if 4S2 and 3D4 as per the rule, it should be like this, but it breaks here. It consider that this half filled or full filled subshells are more stable electronic configuration. Why it becomes more stable, I will tell you later on what is the explanation of that. So here instead of 4S2 and 3D4, 4S1 and 3D5 is more stable. So it is considered. So wherever this half filled of a subshell, outer shell is possible, so one has to consider that one. And similarly for, I think, chromium, then manganese 25, iron 26, cobalt 27, nickel 28, and then copper 29. In case of copper 29, so here again you can see this here 24 5 more electron I have to put. So, in principle it should be 4s2 and 3d 9, but since one electron given there. So, this it will be 4s1 3d 10. So, fulfilled on this subshell. So, here it will be 4s1 and 3d 10. Okay. So, fulfilled or half filled are more stable. So, its explanation mainly it tells this 4s and 3d, this energy difference are not much, okay. They are very close, and that is why this type of, if energy difference is very high. So, it is this type of exchange was not possible. Since they are very close, this type of exchange configuration is considered, and experimentally it gives more stable configuration. So, so this way one can find out the electronic configuration of the multi-electron. So, why I need this electronic configuration? I need because I want to find out the spectroscopic term for multi-electron atom. Spectroscopic term for multi-electron atom okay. So, I think I will continue in next class. Let me stop here. Thank you.